Today, we're going to peel back the curtain on the invisible nervous system of our planet. Seriously, it's the tech that powers pretty much everything we do online, from streaming movies to global finance, but most of us never, ever see it. Yep, we are talking about fiber optics.
I mean, have you ever really stopped to think about how that's even possible? How you can have a live video call with someone on the other side of the world with basically zero delay? How does all that data physically travel thousands of miles, under oceans and across continents in the blink of an eye?
Well, the answer sounds like it's straight out of science fiction, but it's totally real. It's not electricity chugging along a copper wire. Nope, it's pure light, flashing billions of times a second, perfectly trapped inside fibers that are no thicker than a single human hair. Okay, so how do you trap light, and how do you make it bend around corners? Well, it all comes down to this really cool fundamental principle of physics. It's called total internal reflection. Just imagine you're shining a flashlight through a pane of glass. If you hit it at a really shallow angle, something amazing happens. Instead of the light passing through the edge, it reflects perfectly off the inside wall, almost like a flawless mirror. And just like that, the light is trapped.
And this is exactly what's happening inside that tiny glass fiber. The light rays just zigzagging down the line, hitting the boundary and reflecting perfectly every single time. It basically creates this perfect tunnel of light that can guide the beam wherever the fiber goes, for miles and miles and miles.
Now, the secret sauce that makes this all work is in the design. That fiber is actually made of two different types of glass. You've got the inner core, which is where the light travels, and then an outer layer called the cladding, which acts as that mirror. The trick, and this is the whole shebang right here, is that the core glass bends light just a tiny bit more than the cladding glass does. That property is called its refractive index, and that tiny difference is what forces the light to constantly reflect inward, trapping it perfectly.
So, we've got the physics down, but how do you take this incredibly delicate thread of glass and make it survive in the real world? Let's take a look.
Yeah, this is no simple strand of glass, not by a long shot. It's a seriously engineered piece of hardware, designed to be tough enough to be buried under a city street or even laid down on the ocean floor.
Let's just peel back the layers here. Right at the heart, you have that tiny core and cladding we just talked about. Wrapped around that is a plastic buffer, kind of like a cushion. Then you get the strength members. These are often made of super tough aramid fibers, and their whole job is to take any pulling or strain so the glass itself never gets stretched. And finally, you have the tough outer jacket, which is the final shield against moisture, rocks, you name it.
But even with all this incredible engineering, sending a perfect signal across a continent isn't so simple. It's not a perfectly smooth ride. That little pulse of light actually has to face a pretty tough obstacle course along its journey.
So first, let's just remember what these light pulses are actually doing. They're not random. They are literally digital data in physical form. A quick flash of light from a laser? That's a 1. A moment of darkness? That's a 0. You flash this on and off billions of times a second, and you can send a mind-boggling amount of information.
But here's the problem. Take a look at the signal on the left. That's how it starts out. Nice, sharp, clean pulses. Now look at the right. After traveling a really long way, those pulses have gotten all smeared out and fuzzy. The ones and zeros are starting to blur into each other.
This smearing effect, it has a name. It's called dispersion. It happens because different parts of that light pulse actually travel at slightly different speeds inside the fiber. So, the longer the trip, the more the pulse spreads out. If it spreads out too much, the receiver on the other end can't tell where one bit ends and the next one begins. And that means errors, which ultimately limits how fast you can send data.
The second big challenge is something called attenuation. And this one's simpler. It's just the signal getting weaker or dimmer the further it goes. Think of it like a flashlight beam. Even though this glass is insanely pure, tiny little imperfections can absorb or scatter a little bit of the light, causing the signal to lose its punch, mile after mile.
So how do we fight this signal loss? Well, check out this graph. This is basically the playbook for engineers. It shows you the signal loss for different wavelengths, or colors of light. See those big dips? Those are the sweet spots. They're called low-loss windows, and they're specific wavelengths where the glass is almost perfectly transparent. So engineers design their lasers to operate at these exact infrared wavelengths, which lets them send signals for hundreds of kilometers before they need a boost.
All right, so considering all these challenges, you might be wondering, why did fiber optics completely take over the world? Well, the advantages are they're just that good.
I mean, the advantages are just staggering. The bandwidth is almost impossible to imagine. A single cable, thinner than your pinky, can carry more data than all the old copper wires in a city combined. It's also completely immune to electrical interference. Plus, it's super secure because you can't really tap into it without being noticed. And of course, the signal loss is incredibly low. Now, it's not perfect. It's expensive to install, the glass can be fragile, and you need specialized tools and training to work with it.
But when you weigh it all up, the verdict is just undeniable. The pros so completely outweigh the cons that fiber has become the absolute, non-negotiable backbone of our global communication network.
It is truly wild to think that our entire hyper-connected world, our whole digital civilization, is balanced on these incredibly delicate threads of glass carrying information at the speed of light. It really makes you wonder, if this is what we've built in just a few decades, what incredible technology is going to be the backbone for the next generation?